faculty, and now he is currently the professor, and he has very interest. Basically, now he has published many research papers on groundwater modeling, then soil moisture modeling at the catchment scale, and he has published quite extensively, and he is in a lot of important committees at national level and international level. So today we are fortunate that he has agreed to give one lecture on groundwater modeling. So basically, this a case study, say what he has done, okay, at urban level, okay, the groundwater impacts. So I request now Professor Shekhar to deliver this lecture. Thank you, Shekhar, for accepting our request.
Thank you, Professor Hari. Thank you, Professor P.K. Sharma. It's a pleasure for me to be amongst you in this morning. A very good morning to Professor Govindaraju. So very nice. So I will, without much ado, I will just start a quick. I hope I can share open access. Hello. Is it able to? Are you able to see my screen?
No, sir.
Not yet. Is it doing that? No. Privacy. I don't know. It says that. Give me 2 minutes in case. In case some difficulty, I will use the other one. Sometimes. Give me 2 minutes. Sometimes different computers have different problems. Okay. I'm trying. If you permit me to log out and log in, is that okay?
Yeah,
just in case, okay? So that just 2 minutes. Thank you. So I had some difficulty there. I'm trying to open here if I can. Start video. You can see my video, and I'm opening my screen. Let's see, it opens. Can you see my screen now?
No. Yeah.
You should be able to see my screen, hopefully. Can you now?
Yes, sir. Yes.
Thank you very much. So thanks. So I will continue the presentation. It was a few seconds. So what I wanted to use this 1 hour lecture is to give you some ideas on what we have been doing on the groundwater modeling. Like Professor Hari told, I continue with a lot of groundwater modeling of various kinds, constraining the groundwater models with lots of input data and other things, and also as per the stakeholders' requirements, right? So some of the slides I present is based on interactions with several team members which I work with both nationally and internationally, and most of it is credit should go to the students who have put in all the effort. I'm just voicing what has been done. So just to give you, I'm sure you've gone through a large amount of information in this course, but just to complete this overall aspects. So in India we have a wide. Let me see if my pointer is on. Yes. So you see, India has good rainfall regions in the Western Ghats, and on this, the blue colors indicate a higher rainfall regimes. And also we have shadow areas in parts of Rajasthan, shadow areas in Karnataka, where the rainfalls after depleted, the clouds are depleted with rain, we have a drought system. So or initially we had, you're all familiar with Green Revolution, where we invested a lot on irrigation, seeds, better varieties of crop varieties, etc., and cropping changes, including fertilizers. So irrigation was a mainstay in India's Green Revolution. So we built canals, dams, etc. The second Green Revolution in India, we call it, is somewhere post 1980s, where until then the groundwater was not much used. But then we started using groundwater when I was a young MTech student. The whole idea was in the country how to develop groundwater, how to do pump tests, how to increase the productivity. So the focus in the 80-90 period by Central Groundwater Board, various groundwater agencies, develop groundwater. Today we have probably developed too much of groundwater. You will see very soon. So one of the problems is that the groundwater is not so much in these areas in the peninsular India. I say 2/3 of peninsular India is composed of various hard rocks, crystalline rocks, basalts to granites to various charnakites to schist and so on. They have very low storage parameters and also very low transmissivities. This is so that means the yields are very small. So typically less than 1 liter per second, 2 liter per second. Whereas if you are in Roorkee now, probably, or in parts of Indo-Gangetic Plain, you can pump probably 40, 50 liters per second from a well. So which also puts a lot of difficulties for people to use water. But then it was not deterred. People did not get deterrence from this. Lots of government policies and also development of groundwater in the country has led to groundwater being used. So this cartoon is a very impressive cartoon. I hope that we will have another decade of information. This was done by one of the UNESCO works. So the development of groundwater was very small in 1950s India. The diamonds indicate, the green diamonds where my pointer is. So if you see, by then the US was already pumping about 50 kilometer cube of per year of water. Typically, we measure groundwater use in the country in terms of kilometer cube. The reason is you have a rainfall of probably 4,000 kilometer cube. Some of it is getting evaporation, some of it is recharging, and some of it is going. So our interest is to understand how much is the recharge, how much is the storage, dynamic water storage in the groundwater. So they were already pumping 50 kilometer cube. They went on increasing to probably close to 100 and kind of stabilized in terms of use of water. So if you see China, which is a lighter green triangles, which is another big country, I'm just showing the bigger country. So it also started very low, maybe 10 kilometer cube or something in 1950, close to about 100 plus now. But if you look at India, which was also close to 15, 20 kilometer cube in 1950, we are currently pumping 250 plus kilometer cube. This is an older data of 10 years. In this whole place, we have maybe added more wells. So typically we have in the country something like about 30 plus million wells. They're counting them, a lot of surveys and things like that. And we are pumping, probably the groundwater use in the country is equal to sum of all the countries in the world, mostly. So if you say we are 250 and many others 100, 120, etc., and plus add up, so we are kind of one part and the whole world is another part. That means we are extracting the maximum out of groundwater. This is an impressive way of. There are several reasons for the groundwater use getting development strategies and so on. In fact, there was a nice cartoon made by Professor Tenk Bale from NASA, trying to ask how is my groundwater developing in the country. So you can see all the blue areas are where the irrigation comes from canal commands, and the red is all areas with a lot of groundwater use. So clearly you can see that wherever blue patches are where the canal commands exist, where the dams have downstream or major lift irrigation projects and so on. Whereas groundwater got equitably developed in the areas where right now there is no canal. So we call them as originally what we call as rain-fed or dryland areas have become completely groundwater controlled in the current system. Of course, we have patches. You can see very little groundwater use on the northeastern part and also in the Orissa, Bengal, Bihar. There is not so much development in spite of good amount of rainfall. There are several things. Maybe the energy is one of these. So if some of you are following the irrigation concepts in India, you will see that we call this as major irrigation is so much, minor irrigation is another. So I hope this slide is clear. So net irrigated area and minor and major irrigation. Minor irrigation is much higher. Minor irrigation means groundwater and tanks and so on and so forth. Major is by canals. So there was also a nice cartoon made by Professor Ukmanulal some time back showing how the impact the groundwater development has impacted the energy. So today there is a strong connection between how much you can produce food based on the irrigation. Irrigation improves because your cropping intensity is increased. You have an opportunity to do second crop in the Rabi season with when you don't have a rainfall, if you have stocked water in ground or in canals. So the food is very strongly linked to water, especially for increasing the intensity. But the energy is also very strongly linked to the food and water because many of these wells require pumping. And if you see, most of India's pumping happened on the western hem if you see the groundwater use is on this side. So the energy requirement is also increasing because every state is telling more or less many states on these areas where groundwater is used, where the supply of groundwater, I mean, the energy is free to the farmers. They are reporting 25 to 30% of the energy use only for groundwater lift. So that means if India is probably third or fourth highest energy producer in the world, 30% of that is simply going for lifting the pumps. So there is an interest here to look at efficiency of the pump design, hydrogeology of it, to see what is the best horsepowers. There are a lot of things, how to smart irrigation rather than wasting the water and so on, wasting the energy. So you can see that where the groundwater levels are deeper, you're producing more, you are requiring more energy use. So this was a nice cartoon which Upmanlal generated through his group in Colombia. So the idea of to say that is we are increasing the energy use, but bleeding 30% for these. So we need an urgent understanding of the food, water, energy nexuses, which is not only that, the energy which we use is also important for GHG gases, etc. So keeping this overall view, I will give you some presentation of some case studies. So for example, typically any water budget in a small catchment or a moderate size catchments where there are, we can say precipitation is converted into something called discharge, which is the stream flow which you're measuring. The other one is evapotranspiration, evaporation plus transpiration. Another is a combination of whatever is recharge. So you have a runoff, you have evapotranspiration and recharge. So if you combine some amount of recharge which goes as a base flow to the runoff, you get the total stream flow. So I just wanted to say that the combination of recharge to convert to base flow adds to the stream flow. We'll see later. So if you're doing an annual budget in India, this is interesting because we have a dry season and a wet season. By the end, you come back to dry season in April, May, June, or April, May, your moisture conditions come back to the same state what you were in the previous year. So kind of my moisture storage reduces. So we can write. If you're doing a budget, whenever we say budget, it's an integral of time. So when we are doing something over a shorter period, like say Kharif season or the Rabi season, etc., or in a part of an intra-year season, then you have to also consider how much water storage has or water stored in the soil moisture budget. So that means apart from knowing how much is gone for runoff and how much is evapotranspiration, how much is recharge, how much is. So if you look at bigger problems, including satellite pictures of grace, etc., people look at combining how much is the soil moisture, how much is the stream flow, and how much is the evaporation, subtract all of it to understand how much is the grace water levels or water level fluctuations in different grids corresponding to recharge. So this is very a way of looking at it. So that means one of the important aspects is to understand how is the recharge. So this was understood several years ago in India to say that as we are developing groundwater, my recharge also could have improved. In many places, there was a nice paper long back in Science to say in different parts of the catchments in the US, what is the impact of development. As you develop groundwater, you may lose storage of water, dynamic storage may come down, or you create a capacity for additional recharge. That's called the augmentation recharge. So, large part of Indo-Gangetic Plain, there is a large amount of recharge happens because canals, etc., seep to groundwater and people are able to live. That means a canal which cannot come to one farmer the leaks into the groundwater and picked up. So that's how the large part of Indus and Western Gangetic Basin groundwater use has helped in using it. So to make it simple for some of you, the idea of making a simple groundwater budget. Now, when we say recharge here, this component is going to groundwater, and we would like to understand what is a groundwater budget there. So if you want to look at a groundwater budget, typically there is a groundwater level fluctuation is happening, whichever aquifer you're pumping, or if it is multi-aquifer and the individual aquifer analysis, etc. I will not go deep into that. So essentially, one can drive, assuming that if you consider it as a non-flowing system or take a larger watershed with without spatial variations of recharge, and if you ignite water movements for the discharge recharge conditions, the storage change, which is called SY into DH by DT, which is a fluctuation component multiplied by specific yield, should balance all the recharge. The recharge due to rainfall, the recharge due to induced recharges, which is common in, as I said, in some conditions, rainfall recharge, induced recharge, indirect recharge. And then the upward component is the pumping, which is going out. And then you have a discharge underflow. It is possible that if it is a small stream in the first order, second order stream, the water may not even go to the base flow because groundwater level is much lower than the local stream bed. And so it may go as an underflow, you can see here. So that means the recharge which is happening in this catchment may go to the next catchment or much downstream and go out. So some of you are interested, you can refer to papers of Toth and so on, which tell you along the topography how the recharge comes out and so on. That's the reason why we look at isotopic signatures and so on. Where is the recharge for this watershed and how is it going? So not all the water is ending up into the stream. Some part is going as an underflow. So we can put them as base flow and an outflow, which is a groundwater discharge. So it's a discharge term here, recharge term. This is a vertical pumping due to human beings. So in the olden days, probably the pumping was much smaller. But if you go to a forest, the pumping is quite good because you have big trees pumping like wells, etc. So if you combine them nicely, you can make some simple 1D ordinary differential equation, a one-dimensional an ordinary differential equation, for, which gives you specific yield dH by dt, which is the fluctuation component, some factor terming recharge, some parameter relating to pumping, and something is called a net outflow. This is an interesting work because if you carefully look at, there was a nice paper by Park and Parker, Jack C. Parker did with another gentleman, Park. It was published in Journal of Hydrology. He was looking at a simple system like this in an unconfined system without pumping to ask how does water fluctuation happen and how we can use that to understand the recharge and so on. So if you look at operational groundwater method in India, where we estimate groundwater recharge in every small watersheds of about 600, 700 square kilometer, every year there's an atlas prepared in India. The Minister for Water Resources gives is an operational groundwater estimation. Every year we estimate groundwater resource and also label which areas are good, which areas are bad. I'll show you an example. So it is based on the recharge. And so that means we're saying how much is the recharge, how much is pumping, essentially. So some people combined the net outflow, the pumping and outflow together as a component. You can do that. For example, I'll show you a simple example, which is an example which I'm going to show you. So, in fact, there was a nice similar example in Journal of Hydrology by Marshall telling you about the operational approach in groundwater. So, in India. So, here is a small cartoon again for you to show you that we were doing a small town called Mulbagal, very close to Bangalore, Tamil Nadu border, on the highway from Bangalore to Chennai via Chittoor, if some of you. So there is a town called Mulbagal. In Kannada, Mulbagal means some corner town. So the idea was the town mostly depends on, had a population of 60,000 and mostly depends on groundwater. They had tank systems, as you can see here. These tanks have become polluted now over time. In the olden days, the tanks were maintained to have clean water. So because of the pollutants, runoff pollutants, etc., so people don't want anymore use the tank systems for. So the municipality uses large number of wells. Outside, of course, agriculture wells exist. So the red ones are the municipality wells inside the town, which pump and supply the requirement of this water. They have about 100 plus municipal wells, which are running with continuous energy given to them, etc. So the interesting question they have is how sustainable are, etc., etc. So I'm just giving a simple example of how you can convert that with a hand model. So the idea is that if you were to consider the system as some, if you convert that into pieces of various land management units or various groups of cluster of wells, and say I have a system where my groundwater inflow occurs into that parcel because groundwater is moving in the system. There is an inflow into the system. There is an outflow from that system. That means I taken a land use. It's possible that you're looking at a Roorkee campus or you're looking at some region, and you say inflow is coming and outflow is going out. Okay, and then you have a pumping going on in that system, and you have a rainfall which is a recharge. So this is called the dynamic groundwater source. The static water is here. So, in fact, Central Groundwater Board publishes documents saying what is my dynamic groundwater resource and what is my static groundwater. That means my dynamic groundwater resource is where the fluctuations are happening. With the time, it's possible that I am going into my static budget in some times. So, interestingly, you can reapply this simple equation on this. You have the same equation which you saw in the previous slide saying delta H by delta T into SY is equal to R. Q in minus Q out is happening. It's possible that you are here and there is no stream, etc., in a small area. So Q in is Q out are my lateral flows, and there is a QP is my pumping. So you can describe the in and out as a Q net. If you have a small region and if you make a flow net or make a good flow net observations of the system, you can find out what is the inflow into that and outflow. I would recommend that you should see the paper of Marshall, who works with the Bureau of Research and Geology in the mines of BRGM in France. So he made a nice paper of a catchment of 50 square kilometers to describe how it is in Journal of Hydrology. Maybe I can send it in chat box, the paper. So it uses an Indian operational approach. So the idea is that in this, all terms exist of what is happening. Inflow is coming into a region, outflow is going in. If inflow is equal to outflow, groundwater net out inflow and outflow, then this drops out. Otherwise, inflow is more than the outflow. My level can rise or fall depending on that. The pumping can change my groundwater level. My recharge is happening. That's also can be. So one can rewrite this by saying, okay, I have two loss functions and one input function. And here is that this is algebraic. So what in India we do most of the time is that we don't measure every month because they don't have capacity in all the places. Like Central Groundwater Board measures 4 times a year. In the southern states nowadays, all people measure once monthly now, and they are putting under National Hydrology Project more continuous probes, etc. Because going to the field measuring, though groundwater levels are not going to change dramatically every day, but in order to reduce the logistics, etc., the continuous groundwater station. So we have probably 30,000 groundwater stations in the country, and it's a huge task and is a very well maintained system in comparison to many countries because groundwater is important for us. So what is done in, I'm giving you an example of what is done in their country in operationally. This is a simple example of how to use operationally. And if you are interested, you can see groundwater estimation committee methodology, which follows a similar approach. So this is done across the country. So the idea is that this equation is split into two halves. The idea is that you write this equation for the monsoon season and non-monsoon. The idea is like this. Here is a typical observation well in that same location. The groundwater level was about this much in just around August, July, and then around it starts increasing because these are my rain happening. And this is in the month of, we did this measurement. This is measured by one student in 2008 in Mulbagal. So we have this groundwater level rising up to November. In these areas, the rise is usually happens up to November, something like that. I was telling that we have 4 times we measure. We make one measurement in the month of August, which is in the Kharif season. One measurement measured in November. One is measured in January, post monsoon, and one is measured in April. So in August, November, January, April. That covers the 4 times in a year because we are not like January to December calendar year. We have a monsoon year between June to May, kind of. In JJAS, June, July, August, September is our monsoon season, some southwest monsoon. So as you can see, the rains are happening. The rains are stopped now on the southwest monsoon, which is typical for whole country except Tamil Nadu. The rains are in the northeast monsoon. There's some parts of the Tamil Nadu, except Tamil Nadu, most of the country is covered by southwest monsoon. And then the groundwater levels go down. So here is an example of how June, July, August, I was showing you how the rains are going up and then correspondingly the groundwater level is going down. The loss of groundwater here, even if you don't pump, it will not stay. It is going out to the base flows, underflow, etc. If you are pumping, you are taking some portion, you are readjusting the flow, something is going to the underflow, something is being pumped. So the net loss from the system is getting readjusted. Sometimes it could be more because you're pumping more than naturally gradients can send out. So that means we can rechange this equation because we have only few measurements in a year. We can say, let's say 4 I told you, which is what is a national approach. So you have a rise function starting from August to November, which is called delta H rise. And you say that the rise in the water level multiplied by specific yield because you're talking about the volume of water. You multiply a parameter called specific yield, which is like a function of porosity. And then you have this must be equal to during this rise period. Many things are happening on the right hand side. One is recharge is taking place. So that's one component. It could be due to induced recharge. It could be rainfall recharge. And you have a loss function. So recharge and the loss function Q net is inflow minus outflow and QP, which is both are negative for me. I put it. It's possible that Q net could turn out to be negative. That means I have more inflow than outflow. Then it becomes negative and adds to the recharge. Otherwise, typically always groundwater is draining out. We assume that every parcel more water is going out than incoming, especially in the upper reaches. So one can say this is operating over a period of these many months where the delta T is, we call this as delta T times. So I converted the ordinary differential equation into an algebraic equation by simply getting rid of as delta H by delta T. So I can rewrite this equation for non-monsoon as well. So if you do that, in the non-monsoon, the advantage is that you don't have India has a benefit that you don't have a recharge. This is not applicable areas where people in an urban area, etc., where will come back as an application. You may have a recharge of various kinds. So if you don't have a recharge, so you can nicely drop off the recharge factor and say this is the only parameter. The idea is that if you are in some places, mostly Rabi Kharif, good irrigation, let's say you are in areas like in Punjab and things like that, my QP will be the same during mostly in the rainy season and in the non-monsoon season because I have a rice wheat system, or maybe I am in intensity of cropping in irrigation systems, or in urban areas, my QP is more or less the same every day. I pump the same amount of water. So the idea is that to get an idea of a handle of QP plus QNet is one angle. If you know better understanding about the QP, QNet, you can substitute, and QP, you can substitute and then obtain an SY. The national methodology says that estimate SY using the second equation where QNet and QP can be estimated by other means and then apply SY basically delta H fall, and then use the SY back here because SY could change from time to time from the level of fluctuation that SY is decreasing with the, usually SY specifically decreases with the depth. If the groundwater levels are falling, my specific yields are likely to be becoming smaller and smaller as you go into tighter and tighter systems, especially in the rocky systems, 2/3 of the rock area. Or if you are familiar with what is the value of SY and you are not familiar with this, you can estimate this QNet and QP and use this in this equation. So you will see an example like this. You say that delta H rise is so much, delta H fall is so much. That means this has happened in 4 months. This happened in 7 months. You have an SY or about 0.5%. Again, I want to tell you that the SYs in rocks are about 0.5%. If you are going to alluvium, you can use it as 1%, 1.5%, and so on. So and then use these two equations. So I got a QP and QNet in this equation. You can get the recharge from this and say, this is my recharge. So what is telling you is that I had a recharge of something like 106 mm here from the rainfall, a QP plus QNet of 73.68. That means the sum of all the losses in this period, in the whole year, was something like this. So in this case, what happened? I started with a lower water level, ended up with a higher water level than it started with about 30.9 in July. By June, I have already reached 22.41. So if you see, my previous year in 2008 had a deeper water levels, ended up by the next monsoon with a higher water level. That means the delta change, delta H happened between the two in the entire year was positive. That's why my recharge is higher than the loss which has happened. So now this is a simple way of calculating. Next year, it's possible that I started with 22 meters and then go down to 35 because my rainfall was less or whatever. Then the loss function is more than so this is a very simple way of doing it. Every well you can do it. You can do a good optimization if you have parameters. In this, there is no optimization simply. But if you have multiple data and you don't know SY, you don't know recharge, you don't know, you have a data, you can subject it to an optimization. So that kind of models were built. So that's why I showed you this example of this model. So you can use this model like this, where you can say R is my parameter from recharge, DNet is my pumping, and lambda is the total loss function from the system, etc. And make the parameter this to use it in the system. So to close that exercise, just showing you Karnataka, it is the same for different states. So if you look at Karnataka, these are my monitoring wells. You can see how many monitoring wells we have, a large number of monitoring network. And if you look at the groundwater level, this is a typical groundwater level. It may change year to year, but the patterns won't change. That's important. With the time, over 10 years, probably the levels can change, increase, decrease, etc. But if you carefully look at the basic tenet of this, you see that my shallow water tables, the legend here says shallow water tables on the western front, which is expected because you are on the Western Ghats with a high rainfall regime. Then you have a shadow areas in Karnataka where the rainfall is very low, 500, 600, 700, and so on. And you are talking about 4,000, 5,000 here. So these are called the semi-arid arid areas, and more rainfall in the southern part than the northern part of Karnataka. And in spite of that, my groundwater levels are much deeper here. So interestingly, this is a lot of the Bangalore neighborhood groundwater levels loss is because of a lot of virtual water transfers for agriculture purposes. So, for example, Bangalore is about 15 million. It is pulling so much of requirements to the city. So all the milk has to come from the neighboring districts of Tamil Nadu and Karnataka to this. So people are growing lots of vegetables, fruits, all that. So there are a lot of virtual water transfers apart from water uses within this. So you can see that all these districts are bleeding with groundwater supplying to Bangalore. So I call this as virtual water transport. So but interestingly, so you can see that areas which are hotspot areas for groundwater understanding, even though the rainfalls are much better than here, we are losing groundwater here. So that's the reason why a documentation is done. Like I told you, that National Atlas gives you, this is one example of it. Every year they publish it. These are called, the colors indicate that if the recharge is higher than the development, That means if my recharge is about 50-60%, no, my pumping in a particular watershed of about 500-600 square kilometer is about 50-60% of recharge, then I call it as safe. You can refer to the national methodology. And if it is greater than 60%, between 60 and 75%, we call it semi-critical. If it is more than 75% to 90%, it's critical. And still, if it is going more than 100%, it's overexploited. That means my pumping is more than the recharge. So that means I am losing my water much larger. The idea of putting 60% is that some water is recharged into this. You don't develop more than that. Rest of it is you leave for the water to go into the streams, base flows, etc. If I'm extracting a lot of groundwater levels will go down, the water to the streams will die, and many streams will be dry. So today, many tank systems are dry here. Many rivers are dry. They are trying to revive some rivers closer to Bangalore. There is a river called Arkavati, which used to flow. Bangalore used to get about 100 MLD from there on that river. Now there is no more water in the river. It's dry bed. So you have to look for farther locations to bring water. So this is because you have used one part of groundwater which used to go to stream. Now you are using it's the same water essentially. So I will go back and say they are trying to do this exercise by saying a national aquifer management program. They have at CGWB, Central Groundwater Ministry of Water Resources. The idea is how do we manage groundwater? So how much we know? What are our aquifers? I mean, it's not only about the groundwater levels. What kind of methodologies we have to do, because if you want to do some kind of intervention of recharge and so on, you need to know how are my fractures, where is a better way to locate, where do we induce the recharge, and so on. So you need to get a better idea of hydrogeology, geology, the geophysics there, and so on. So they are looking at all the hydrogeological approaches to understand and map the aquifer so that the interventions can be made much better. So that is the part of so there are several questions which are at the national scale happening. How much, because we're increasing our irrigated area day by day, rain-fed areas are getting more and more farmers are adding 30+ million wells in the country. So how is this irrigation in rain-fed areas? I call rain-fed because command areas have water coming through canals, etc. These are upland areas. How sustainable they are? There are questions on can we continue to sustain the crop production in these areas? We have increased our crop several times more from earlier days. And can we continue to go without depleting and polluting groundwater? Is the groundwater improving the farmer's livelihood, which is an important, there is a national rainfed authority in India, and they are looking at livelihoods, watershed management practices, etc. So there are lots of questions on policy, water management of groundwater because you have developed all this. So which requires a lot of understanding at various levels, regional scale, small scale, technologies, and so on. So I'll give examples of a simple crystalline rock aquifer. How does it look like? So typically a crystalline rock aquifer, like where you are standing in Bangalore or in the Deccan Plateau, called the Deccan Plateau, is the flat plate. Which has come from Africa, so it is attached to the Indo-Gangetic plate. So this plate has a mound like this. This is an uplift effect, and so you have a mound, you have a high rainfall regime, and then you have a system like this. So if you see that below the rock, which is a granite or a gneiss, they have a lot of fractures. You can see occasionally a huge, big vertical flows, shear zones, and so on, which can transmit a lot of water down. So if you are mapping these shear zones, in these areas, so if you have to push water, if you have a nice shear zone, you can push water into this. But the water penetration here is very small. So you have a small soil on the top, which is very little soil. And then you have a saprolite. Saprolite means a weathered zone, which is weathered by the parent rock. And then you have a fissured zone where you have fractures. And then you have a very tight rock, which is completely, probably very few fractures. So if you see a cartoon here, you will see how the fractures are occurring. This is a cut section in a mine nearby. So the whole question is that how is how are these groundwater is controlled. So how whether the good connectivity exists, we take transmissivity or hydraulic conductivity, how good is connection at a watershed scale or tens of kilometers. Should we consider it as a bucket or should we consider this as a connection, and so on and so forth. These questions are still happening. Interestingly, what happens also is that it's not necessary that everywhere groundwater is used. It is so. As an example, here I'm showing this is a river called Kadini, which is a tributary to Kaveri, and you see that uh, not all parts. This was we did a mapping of the entire river by using groundwater level measurements. It's a very pedestrian work of going around and making the map with every village to get a documented evidence of how the groundwater level looks in the basin. So now, if you look at it, because typically, I want to again emphasize that the monitoring network, even though very good in the country, is not so good to make a map of a good river basin map, because we have about 80 square kilometer one monitoring station in the country, or 100 square kilometer. Average is 80. In some places, it is 100. That means every 100 square kilometer, you have one well. So if you take, that's the reason why we said groundwater assessment is made at every 600 square kilometer or 1,000 square kilometer, so that you have at least half a dozen wells, fluctuations you can take and make an assessment. If you want to make an assessment over a 5 square kilometer catchment, which is 5,000 hectare, or even a much smaller catchment, 1 square kilometer with 100 hectare, typically micro watersheds are 500 hectare and so on, or a watershed which watershed street are 5,000 hectare, 5 square, so 50 square kilometer and so on. So if you are looking for such kind of watersheds, you don't have information. Even if you take a 5,000 hectares, you don't have a monitoring well in that. So the idea of doing this pedestrian mapping is one shot to know which are the areas where the problem is a groundwater problem. So we can see that some part of this area has a bad groundwater situation where the levels are already deeping in this area. People are using a lot of groundwater use. Whereas there is a river here, which is the Kaveri River. So people have canal systems, etc. Not so much of groundwater use. So you can see the upper part of Kerala, which is a district of Wayanad and so on. So why I'm showing this is we're doing some work there, but that's okay. But important issue coming out of this is that you should look for probably the something is hiding. So I should give me a minute and I will try to pull this out so that you get an idea. Okay. So the interesting point of this exercise is where is my splitter? So if you carefully look at it, if it is a small catchment here, which we are monitoring with about 200 wells to understand the groundwater connectivity, etc. Interestingly, the watershed, this is the nearest river which is in the neighborhood where the topography is falling down. The catchment which we are monitoring is somewhere here where my red dot is showing. My groundwater levels are going down to the valley. So you can see groundwater level in the valley is more deeper than in the topography relatively. That means higher levels have typically hydrology tells you that groundwater levels are deeper at the hilly areas. Go to the valley, you have, because groundwater is going as a base flow. Here it is a completely an inverted situation. That means these people started pumping, they had better soils, they had a better probably investment plans and so on. They started pumping groundwater before, and as they started pumping groundwater, the groundwater levels went down. But then they are not impacted because the groundwater is flowing more and more as the gradient is increasing. Previously, the gradient was like that, and now the gradient is like this. So Darcy is working for their benefit. So these guys are able to pump more water, and that means these are the recharge for these people. So this is called the upstream downstream controls on groundwater. So if these people are doing lots of watershed management, they are very thankful to this because these people get benefited of this water here. So plus also interestingly in hard rocks, the interesting, as I told you, like specific yield, the yield also, which is linked to hydraulic conductivity of the fractures. So if the groundwater levels, if you can see the yields, borewell per yield. So if my depth to the groundwater is shallow, water table is up, then I get a higher yield. So slowly as you go deeper and deeper, people put wells up to 200 meters, 100 meters and so on. When they put the well at this deep, you get much lay. Here it is shown in feet so that you get a rough idea. 200 feet means something like about 1/3 of it. So in terms of meters. So you have 200 feet. or about something like 55 meters. So you get a very low yield of 0.5 liter per second. So that means depleting groundwater has no benefit. One needs to look at management, artificial management plans. So we monitor about 200 plus wells for the last 10, 12 years now. We started in 2010 to understand various things, looking at controls on agriculture, looking at connectivity, etc. So I'll show you an example of that. So the area looks very similar to this kind of setting where you have various types of crops. Unlike one type of cropping systems we talk about, we have multi-cropping systems here. So people use, every farmer uses different crop. In 1 square kilometer, we may have 30, 40 crops. One is growing chili, one is growing sunflower, one is growing finger millet, one is growing some other sorghum, and so on and so forth. So it's a completely dry land agriculture with a groundwater substitution. So as I told you, how the system will look like in the higher relief in these areas. You can see the rocks like this. That means the unweathered rocks are also open after the erosion happens. You can see one stone sitting over another stone, which is what happens underground. You may have veins like this, which can be a good weathered veins, which can produce a lot of recharge. And then you may have a fractured granite and a very fresh basement rock at some point, maybe 30, 40 meters deep. And so I'll show you in another cartoon. So the idea is that if you have a monitoring network going on, you can make a good assessment of the recharge. So an example of that is done by using a model. We have I told you that we can use that simple model to get what is happening to the groundwater recharge. So what you are seeing simulated groundwater levels and observed groundwater levels, and ask what is the recharge, what is the pumping, how is my pumping evolution. That means you have parameters of recharge and you have a parameter of pumping, and you can ask how is it, etc. If you have more wells in a small watershed, you can use all this data and ask what is the standard deviation and so on. So this exercise we continued for some time. Then slowly we figured out that the life is that the groundwater levels were going down for some time. In the recent past, they started rising because we had a huge good rainfalls for 2, 3 years, which is very interesting because you lose about 30, 40, 50 meters of water stock in a particular place. We were always worried that what will happen as the groundwater stock, you'll see secular declines in many parts of the country. They'll say groundwater levels are declining. So here also the groundwater levels are declining in over a decade plus. And then suddenly we have a huge rise in groundwater level. So if you see the map of groundwater table in 2010, it was like that. Slowly the areas where people are pumping to the eastern part was going down. Yellow colors or hot colors means deeper water tables. By 2017, we had lost a lot of water in the eastern part of the catchment. And then, and of course, there is a forested part here, which is supporting this catchment. And then again, by 21, we are coming back to the same situation as this. So the life is our change. So you can see the contours, which are interesting. So the question was, because you had a huge induced recharge due to good rainfall, you could also ask several questions. How is my recharge behavior over years? So if you see in the previous cartoon, you saw some simple recharge here. So you see 5%, 7%, 6%, 8%. That's the kind of recharges. So if you are interested, you can look at a paper by Florkey and others, try to do a global recharge assessments, global. So the idea was to see such a high change of recharge, would it help? So we looked at various issues. One was to ask the connectivity issues. How is groundwater connected here? That means, is it moving between, is it the recharge local, or is the recharge here is moving to here? If so, this could be about 10, 15 kilometers length. How does it impact? This is important because if you are doing models of gridded models in the basin like Kaveri, etc., you are interested in running the model at 10 kilometer by 10 kilometer or 5 kilometer by 5 kilometer, which is coming from various climatological grids. Today, Indian Space Research Organization wants all the products at 5 kilometer by 5 kilometer because they can produce all the related databases. So considering that you have this information, we were looking at what is the connectivity between the levels. So you can see that as the water tables decline between two locations, the connectivity is getting deeper. When the water tables are rising, they become closer to each other. That means there is a huge mixing you're mixing reactor kind of a thing. So you have a more mixing is happening as they join together. Otherwise, they separate and act as two separate region. That means lower aquifer, upper aquifer, they are not well connected. So something like that. So that means there are so you can see that the disconnections are happening. That means there is no vertical mixing so much or lateral mixing. With the time when there is a good recharge, there is the mixing. So the opportunity to study this is because you have a secular measurements in the system. You can see similar ones. So this led to trying to ask the question, how do we model this? How is the connection and how do we model this? So there was an effort done. If you're interested, you can see this, where we were looking at under what conditions you can model this as one-dimensional. That means not connected, only vertical, like a lumped model in time fluctuating. Whereas you have a two-dimensional model where you have, so we use a stream tube approach to model because we have a lot of data and try to see how is the connectivity in the system. This is the reason why this connectivity was. We wanted to look at later water quality issues. I have a nitrate issue coming out here, and we wanted to see how the nitrates are flushed out. What is the residence time of nitrates in the catchment? So, but then this also has helped us to look at, since groundwater levels went up very quickly, we wanted to see how is my recharge? Is it induced by the water passing through the soil, or are there other indirect recharge mechanisms playing on the role? Because when you have a high rainfall, what happens typically? You have a lot of runoff. The runoff will go into gullies, into ditches, into everything. But it is interesting that, as you can see, I showed you the hard rocks where you have places where there is a potential possibility for recharge. So soil may not be a good recharge location there, but the water which is running away may recharge. So you can say this is not a typical atypical recharge, a fluvial recharge. That means a flow component is helping a recharge. So you can call it as, some people call it as indirect recharge. So extreme recharge, the impact of extreme events is also interesting, because traditionally hydrology is generally belief is that extreme events produce a lot of runoff, but not very understood about what happens to the groundwater recharge. So the idea is that how does this recharge play out is an important question which we are looking at. So there was some work done on this to really look at what is the recharge during this period where there is a high events, and we found that the typical normal recharge happens in this way. That means if I want to look at annual recharge versus annual rainfall, you can plot it somewhere, it cuts probably 150 mm or something, where you will say that about beyond 100 mm rainfall you won't have any recharge. That means it's not going to abscess at zero. But then you have an extreme condition where you have an excess recharge coming from induced recharge or indirect recharge can be like this. So that means if you have models like this, to be able to, even a simple model to say under these conditions of rain or these kind of intensity of rates, we have a different recharge, which is a fluvial recharge. We have a different, so we can in future years, we can have two types of recharge models, one for typical recharge, normal recharge, and another one for, so you can see some work which one of my students was looking at high episodic groundwater recharge events in tropical hard rock systems. I am trying to quickly come back very quickly. I think maybe I have 5-10 minutes, Hari. So one of the interesting aspects for you is also how to look at groundwater level mapping. If you want to do a numerical model, you don't have enough data in the country to make a good groundwater level, initial groundwater level. How do you generate initial groundwater level? That's a big problem. So if you are interested, you can look at some of the work done in the US. There's a nice paper by a team looking at interpolations of groundwater using several secondary variables. So topography, some other parameters, and so on. So Reed Maxwell from Princeton University has been looking at improving the groundwater models for a long time. Right now, he teaches at Princeton University. Previously, was at Colorado School of Mines, and so he made a nice map of groundwater level map of the whole United States at probably 1 square kilometer grid or something like that. So you can imagine how good, nicely made through interpolations. So the idea is that how do you interpolate? So that means if I have 4 points, 5, 6 points here, how do you interpolate? See, the interesting point, in the olden days, there was no problem. So I'm showing you a period of, this is a small taluk in Karnataka, which is called Chiknayakanhalli. one of our minister comes from here, agriculture minister. And so see the groundwater levels on an average taken at few points. These are the various points where the groundwater levels are measured over a long period of time. These were measured from 1990, you can see 80. So the groundwater levels are slowly like this going around. Stable period, because my groundwater levels on average, the pink one is tells you the standard deviation among these wells. The mean is here. The standard deviation mean is gives you an idea about what happens to the variation. Now you can see as you are going into periods of post 90 when groundwater is developing, there is a high standard deviation. The standard deviation is telling you that some areas my groundwater levels are going down, some areas my groundwater. That means the non-uniformity of the. So if it was something like this, I could have taken 4 wells and interpolated nicely my groundwater level. But here I can't do it because it is impacted by anthropogenic sources and so on. So there has to be some other method. If you are only using topography, etc., you might miss this concept of what is my initial. So if I want to model it at every 5 square kilometer, this could be a 1,000 square kilometer area. And if I want to model this, I need to know how it is to be modeled. One second, just in a class, please. One sec. So if you want to look at the period of 80 to 90, this is how my pumping was very small. My recharge was something like this, 4 mm or 5 mm and recharge, so very small amount. Whereas in the later part here, we're talking about draft, the pumping we call is very close to recharge, nearly 90%. So my discharge has decreased. So there was a nice paper by Professor Govindraju is with you. He was working very closely with Sophocles long back in Kansas. So Sophocles wrote a nice paper in Kansas in some of the river systems, how over 20, 30 years the groundwater development has depleted base flows and things like that in some parts. So here is an example where my discharge from this system to the river systems was something like about 50 mm. Now it has become 7.76 mm. So that means my rivers are bleeding. They don't have enough water in the system. That means we are reapportioned the water which goes to into being pumped. So the interest is to look at how do we make. So if you were to make a map of this by using a pedestrian mapping everywhere, you will figure out that some areas I have deeper water table, shallow. This can be done across the board by doing an exercise, working with agriculturists, etc., so that we have a country level map and then improve it further by using some methodology. But this is a tough task tasking. So here is an example we did with probably 300 wells or something, collecting data with many points. But this is not possible. The current network is too coarse. We need to find a better way. So I'll give you another example of how you can use with evapotranspiration. So this is not published, but this is an example to give you. We're looking at it. So the evapotranspiration was estimated by various means. We have other ways. This is an interesting subject on hydrometeorology. So I had a former student who teaches now at IT Bombay. So looking at evapotranspiration mapping. So we make a evapotranspiration estimates at the India scale. We have 5 square kilometer evapotranspiration and 1 square kilometer. So there are global products also. Why we made it? Because we wanted to use our flux towers and so on, which is not easily available to everyone, and create a good database of that. So you can see areas with the low evapotranspiration and high evapotranspiration in a year. So you have the Gangetic Plain where 1200 mm of evapotranspiration happens. So you can use this into a curve called Budikow curve. I don't know if some of you are familiar with Budikow curve, but the Budikow he was an agrometeorologist or hydrometeorologist, looking at ratio of actual evapotranspiration to precipitation, potential evapotranspiration to precipitation. So in a semi-arid systems, you will assume that evapotranspiration can't increase more than precipitation. So maximum 100% precipitation. So water limit is here. That means if all the rain is evaporated, my evapotranspiration is more. This side is called potential, because potential is a climate. I can probably evaporate in this climate probably 2000 mm. Based on climatic, that means that much water I can. So this tells you that my current precipitation is 100 mm or 800 mm. My PET could be twice or thrice of it. So in this case, etc. So as you come to the humid zone, That means if you're going to Northeast or if you're coming to Kerala and things like that, your rainfall is more. Maybe you have 5,000 mm rainfall, but you can only evaporate 500 mm. So that means your evaporation is limited by the energy limit. So here, if I'm standing on this at 0.5, I can only evaporate 50% of my rainfall. I can't evaporate because my energy limit. So we say that this is the energy limit and this is the water limit. Anyway, the interesting point is this Budico gave a curve saying that if you are on this line below line, means that your evaporation is lower than this. It's good because anything which is lost out of the catchment is either felt in the runoff or as you go back to our old equation, precipitation is converted to evaporation and recharge and runoff. So if you are here on this curve for that particular precipitation, this above this 1.0 precipitation is going either into runoff or recharge. But when you take several watersheds and use this exercise to calculate, you see several places my evapotranspiration is more than precipitation. What does that mean? It means that these people are mining water, groundwater. So they are pumping groundwater more than apart from the rainfall they have. So they are on the negative side. So that means my earning is much smaller than my spending. That's the kind of situation they are in. So this means that this is a good index to look at how the groundwater levels are there. So you can use this as an index to. So we did an exercise of trying to say how does over a 10-year period, if we take an index and say how is my evapotranspiration looking at. So you can see areas with the lower evapotranspiration ratios will be my groundwater level depth will be smaller. But as my evapotranspiration precipitation ratio is increasing and my depth to groundwater level is increasing. So these are several micro watershed where we have documented the groundwater level and compared. Interestingly, you will see evapotranspiration precipitation ratio also higher if you are in a canal command area because you have unlimited source of water, you're evaporating, you're growing a crop like paddy or something or paddy plus something, you are evaporating about 2000 mm of water and but rainfall would have been very small there. So that means you are receiving water from some other source and source water, and so that also tells you. But these areas cannot tell you about groundwater. Of course, my groundwater level could be very shallow there because my water logging, etc. So one can use this kind of metrics to understand about groundwater purposes. So maybe I am beyond the time. Hari, what is the state?
Yeah, you can finish. So there are another 5 minutes.
Okay. So I will not spend much, but I'll give you another example going into urban groundwater, which is also an interesting area. I showed you about agriculture issues, something to do with urban groundwater issue. Bangalore is, as I told you, is an important city. We have several, maybe close to 0.7 million wells, 7 lakh, 8 lakh wells in the city. We are about 15 million people. Every household is trying to depend on groundwater and industries and other sources. So it is located just on the proximity of the Kaveri Basin. It's not exactly a part of Bangalore is in Kaveri Basin, another is in another basin. That's the edge of the basin. So if you look at Bangalore like this, you have one river which is going. This is not part to Kaveri. This side the river is going into Kaveri. So it's like Bangalore is like a you can say some kind of a hill, half orange hill. You invert an orange and you have a half orange hill. So the interesting point is, of course, it's sloping down this side and sloping down this side. This goes to a river called South Pennar, and this goes to a river called Kaveri from here. So the western part of the Bangalore is going into Kaveri, draining. The eastern part of the Bangalore is draining into another river which goes here and drains out, which is called South Pennar. So interestingly, the groundwater development has taken place a lot, and there are a lot of questions. What happens to every ward? What happens, etc. But what is interesting in urban areas is that you not only get water recharge from the rainfall, you are also paving, you're doing a lot of alterations. So how does this recharge will happen? The urban flooding happens most of the time because water can't run away due to rainfall, which is my colleague Professor Pradeep Majumdar is looking at. Often in the olden days we didn't have flooding, but now the water can't run away because all the areas are blocked. So this urban flooding is a boon to groundwater. It is like induced recharge can happen in those areas. So we are looking at what happens to the impact of the benefits to the urban flooding, not benefits of urban flooding, how to look at the urban flooding, can we monetize into something. Also, the leakage from water supply and pipelines is an important issue in this, plus infrastructure where you build a lot of deep foundations which do not allow groundwater to go. We have metro lines which are not allowing groundwater. So they're intersecting with groundwater flow paths as well. So to just give you an idea, the land cover has been, you can see it's a completely land cover got changed in an area of about 800 square kilometer. You can see the population, how is the population in the core areas versus outside the core areas, how is the population. More importantly, you will also see who is using groundwater. So household percentage of household using borewell. So if you are in the brown area, very few, only 5 to 10% of households use groundwater because the water supply is in the core areas. This is a pipe network of the system, a GIS pipe network. So outer areas, they don't have any other source, but they use groundwater. But remember, Bangalore is like a half orange. So outside areas on a lower valley, middle of the city is in a higher one. They supply water to them. They don't use groundwater. So the recharge groundwater can go to the outside, right? So you can have all kinds of things. So there are lots of issues on what is the leakage of pipelines. So I just put an example, which is happening more and more nowadays. In large parts, many water supply main pipelines leak. And in Bangalore, government is saying about we lose about 35% of water. This is not 100% loss, but it is a loss unaccounted for also. So one needs to calculate how much it is. So the pipelines are leaking because they have joints, and with the changes in the topographic level, many times the soil is a lot of disturbances. Trees are disturbing them. So all of these will change, leakages happen. So you can see large cities around are leaking a lot. So that means this is an extra resource, which is 24/7 resource to the groundwater, unlike rainfall, which is only 3 to 4 months. So there was a nice, there was a Professor Howard from the UK was writing saying that in many cities in the Europe, etc., the water levels are rising and causing subsurface flooding because for Oxford is a problem. So even though we're not using groundwater in some cities, in some of these European cities, they have to manage to supply water out, remove the water, otherwise, or the leakings, pipelines, etc., are causing waterlogging. So this is what he's trying to say. So in order to understand groundwater, when we looked at, we have very little monitoring by the state agencies. They had 5-6 monitoring stations. As I told you, 80 square kilometer, one monitoring station. So Bangalore, 800 square kilometer, they have about dozen monitoring stations. That won't help solve wards which are about 200 wards in the state. In the city. So we created a nice monitoring network. If anyone is interested, you can type Bangalore groundwater levels. It will take you. You can see the water levels online. This was done for a few years, but we don't discuss. So you can click that. You will get a rainfall and groundwater level patterns there, so that it gives a rough idea to the people there. What are my groundwater levels there? So, but more importantly, what we did is you used this data by creating a 5-kilometer grids. We created an entire Bangalore into 28, 30 grids. In each grid, we have about 5 stations. So that means 5 square kilometer grid is a national grid requirement, and put a few stations, monitor it over 3 years. Through a project called with IAM Bangalore and Stockholm Environmental Institute in California, Davis. And then we developed a groundwater assessment. What we get out of it is to say what is happening to the demand, and what is the amount of pumpage, and what is the actual recharge from rain, and what is the recharge from other sources. So you can see that my groundwater demand is so much MLD. This MLD is satisfied by what other sources I'm getting. So if my recharge is satisfying from a rain, there is very little recharge. But recharge from anthropogenic sources means leaking pipelines, etc., etc. What if you combine that? You will ask the question whether my demand is satisfied or not. So if you only compare with recharge and rainfall, you will say Bangalore is going to hit the dust or something. They will write cartoons by newspaper. But not looking at recharge from anthropogenic sources could be like leaking pipelines, leaking wastewater pipeline. So you can see that the demand versus the situation. So we try to look at it and re-put that and say also what is the flux, lateral flux to the periphery zones. So how much of water goes from the center of the city where the usage is very less, but a lot of leakage by pipelines? How much is going to the lateral areas where there is no water? That means the same water is recirculating in this domain. So the four areas are here where pipeline water is supplied, but these areas have no water, but they are groundwater use. Because of the topography and the gradient of Darcy is there, what is happening? So all this is put into a cartoon before I stop. The cartoon here is tells you that the local rainfall is about this one MLD. If you want to combine it into MLD, in so much of MM, and so much of MLD is available because most people want to say how to harvest this MLD, etc. And the water which we bring from Kaveri from far away, which is a very costly water for us, is about 1340 when we were doing this exercise in January 15 from the local water utility. We got 1340 MLD. So we're bringing so much about 1400 MLD to the city. Interestingly, we lose a lot of water. As I told you, we lose nearly 25 to 30% as a leakage. So the groundwater lifted from the city is about 827. So the metered water supply given to the people in 643. So you are bringing water from 1340, but finally the metered money is only 643. In this, non-metered is also should be considered because this is a very large component. So that's why 35% is the leakage. So recharge from supply of leaks is this much. Recharge from rainfall is very small. And there's a base flow. Today, what has happened is all the lakes are full of water. All the streams which go out of Bangalore are full of water because they have a lot of wastewater in it. So once upon a time, the water is not contiguous because we have always, so drainage, rivers draining Bangalore are full. If you are going on the Mysore road, you will see lots of water flowing. So the base flows are increased because of wastewater entering into the system and so on. And so if you relook at the whole thing, considering the leakage of water supply pipelines in a city like Bangalore, it doesn't look unsustainable. But the day people will start not using this groundwater, or if people stop, the groundwater levels can come up. This could be a problem for flooding. It can be a problem for our underground infrastructure. It could be because our metro lines are below. They have a similar problem in Tokyo and so on. So I stop here. These are interesting applications where one can look at how to model. This was done with a model of our own model. We have a model called Ambas, which is now even linked to a model called Vic. Vic Ambas is being tried in Gangetic Basin, in Kaveri Basin, and so on. Very similar to the models which were done, ModFlow versus SWAT. But we are using a Vic Ambas. Ambas is our own model, which is good for base flows analysis and so on. I stop here. If there are any questions, not stop your coffee and because your session is up to 11:30.
So please, if you have any questions, please then go to it. Yes.
Moscow, I mean, we will be using Contaminant, but the Bangalore area is totally of outdoor region. Then, I mean, what is the governing equation for the outdoor regions?
Sorry, I could not.
I think you come.
You can repeat the question. You can repeat the question.
Yeah, please. Actually, what we want to say is because it's Bangalore is characterized by the fractured aquifer. So
As you can see behind my screen, you can see the rock, right? That's how it looks, Bangalore. Behind, as you can see my picture behind. Yeah, that is underground. What is above ground is this.
So he's asking if one has to use ModFlow for solving groundwater problems in Bangalore area. How do we basically what are the things which have to be taken care while the data?
So I told you that typically we looked at connectivity of these rock systems. The rock systems are well connected if the groundwater table goes down very much on that particular years. Let's say we are talking about a low rainfall regime of, in India, rainfall occurs in spurts, 10 years or 15 years of low rainfall, another good year. So if you look at IMD data over 100 years, you will see events of good rainfall and bad rainfall. So these are occurring over decadal scales. So if the rainfalls are lower, my groundwater levels are going to be very, very low because groundwater levels are depleted by use and so on and so forth. During that time, the connectivity is poor. Needless to say, because my water is going into the rock, which has lesser and lesser fixtures, my transmissivities are becoming lesser and lesser, my yields are becoming. So it's essentially, you can model it as a vertical dimension model. That means every house you can model it as an individual. What is the recharge? I am inducing recharge, I am harvesting water, I can use, etc. But when water levels come up in some season, they have a good flow also. The connectivity improves. So that means I can't flush away my salts, I can't flush away my bad water through groundwater so easily in those some periods. In some periods it. So that means using that as an information, you should know when to model the lateral flow component, when the lateral flow component is small. That's one point. That means the transmissivity, hydraulic conductivities, to understand what is a weather zone, what is, if the water is in the weather zone, you need to consider the weather zone model. If your water is only in the fissured zone, you need to consider only for the fissured zone model. You don't bother about where. So yes. So this is one aspect as far as lateral connectivity is concerned. Topography also drives. I told you the topography makes how much lateral transfers happen. The other important parameters are how is people using this water and how much is water loadings coming under the system. The loadings are very important. For example, if my nitrates in area are increasing, that's because I'm adding fertilizer. So loading is an important function, like you look at in structural engineering, load versus deformation. So load is an important information of how we are loading in terms of what is rain, what is recharge, what is induced recharge, and all those. So looking at interesting features of those becomes important. For example, I showed you about extreme event analysis. So our flooding is happening, and how does the flooding in the city will improve the groundwater recharge in those periods of, usually flooding happens in periods of November, December in the city, because you have storms coming in the Bay of Bengal. There is a huge rainfall, and not the monsoon ones, but the ones which happen suddenly, the water levels rise. And so the groundwater levels are also telling a story of how the recharge is manifested due to induced recharge components are indirect. So you need to apply your model suitably. It's not like a one fits all, apply a model and things like that.
Thank you,
That's the
Shekhar.
complexity.
Okay, thank you, Shekhar, for the lecture. Okay, I will catch you later. Huh? Thank you.
Thank you. Thank you.
Thank you. Thanks for your time.